Welcome to Excel 2013 Statistical Analysis video number 39. Hey, if you want to download this Excel workbook or the PDF file, click on the link below the video. Hey, this video is going to be all about the normal or bell probability distribution and this bell curve. Now, we're going to start off talking about this distribution over here in the PDFs. Then we'll jump over to Excel and do a bunch of calculating. Now, here's this curve. And really, it's the x along here, whatever continuous random variable you have. But when you plot this, it's like a line that extends all the way towards negative infinity and positive infinity, always getting closer and closer, but never quite touching the x-axis. All that area under there is equal to 1. It's split directly down the middle, symmetrical on both sides, with 50% on the low end and 50% on the up end. All of the area, of course, is 1. Now, there's actually a family of normal probability distributions. Now, as long as you plot the frequency polygon or our histograms, we're going to look at histogram. As long as it looks bell-shaped, then that's the shape of your distribution, right? And you can use the models we're going to learn in this video and in this chapter if the population data has this bell or normal shape. Now, later we'll learn about the central limit theorem that will allow us to take samples. But for now, it's all about looking at the population data. So for example, cereal box weight coming off of a manufacturing filling machine or a bag of lettuce filling machine, those tend to be normal or bell-shaped. Salaries tend to be normal or bell-shaped. Sometimes test and scoring situations are bell-shaped. Now notice here, this is an example where we have mu equal to 250 grams with a standard deviation of 2. Here's mu equals 300 grams with a standard deviation of 3 grams. Here, the salary for a month is 3,000 with a standard deviation of 400. Here, it's 3,000 monthly salary with a standard deviation of 100. So the standard deviation will actually determine the height. And if you remember, standard deviation is the spread in the data. So it makes sense that there's less spread because all of the data points are clustered right along the mean, median, and mode. Now let's go down and talk about some important points. Lots of different normal distributions. Mu determines the location on the x-axis. And we'll look over in Excel. We'll look at an example of the bell-shaped curve sliding up and down. But it means it could have this exact same distribution. But down here, you could see there might be mu equal minus 10 or mu equals 0. Or mu equals 10. And in all these examples, I hand drew these, but they're all supposed to be exactly the same distribution, meaning the shape is standard deviation 2. So mu will determine the location this way, and standard deviation will determine the height or the shape. Now, the highest point in the middle is where the mean equals median equals mode. That's part of the definition of a bell or normal curve. As we mentioned, number 4 down here, normal curves are symmetric both sides, and curve extends without ever touching the x-axis in both directions to negative infinity and positive infinity. Now, you remember we talked about standard deviation. So then when you get past 3 standard deviations, then it becomes really unlikely, even though theoretically it goes in both directions. We mentioned standard deviation determines the shape or height. The bigger the standard deviation is, the flatter and more spread out. So here, there's a little teeny curve right there. That's standard deviation 2. They both have the same mean there. But this one is standard deviation 8. So it's much flatter and more spread out. All area equals 1.5 on either half. And finally, we want to remind ourselves of our rule we learned back in Chapter 2. Now, our empirical rule or normal rule will say between plus or minus 1 standard deviation, about 68% of the values will lie. Plus or minus 2 standard deviations, about 95%. Plus or minus 3 standard deviation, almost all the values. That means when we get past 3 standard deviations, it's very unlikely. And remember, we cannot calculate probability for any particular x, only between 2 x's. Now, let's look at the function here. And we don't have to spend too much time on it, but there it is. This determines the height. And here it all is here. When we use our Excel function, when we use 0, it'll determine this. When we use our 1 as our last argument, it will calculate cumulatively from the low end. And you can look through the rest of this if you want. Very important, we got to also remind ourselves of z, because everyone's going to be talking in terms of number of standard deviations, and we know that's what z is. We call it a standard, normal, random variable in this chapter. Earlier, we just called it z and talked about it as number of standard deviations, but that's exactly what it is here. Now, for our first example, we're going to look at points on a test where the mu, or mean, for the population is 74 and the standard deviation is 10. So if we add one standard deviation, we get 1z, or 84. If we add 2 standard deviations, that's 10, 20, we get 94. If we subtract 1, we get 64. Subtract 2 standard deviations, we get 54. X and z, you can use either one you want when we're using Excel functions. And we'll look at both of the functions, again, to calculate probability. Now let's scroll down and talk about the Excel functions. When we have x values, we can use NORM.DIST. We give it the x, the mean, the standard deviation. And here's the trick. When we give it 1, it gives us all the area from the low end up to the x we put in. Now, this is similar to last chapter when we did binomial. Remember, it went from the low end up to the x, but it added the column heights. Here, it take from -infinity all the way up to the x value and calculate the area under the curve. So when we're calculating between two values, all of our formulas will come from the fact that it's going to calculate from -infinity up to some x. If we want to start going on the upper end, we're going to have to do 1 minus. All right, so 1 cumulative distribution function, that's the name in the argument. It really returns the area probability from -infinity to the x. If we use false, it does not calculate probability. It calculates the height of the curve at a particular x. It's not probability. This is what we'll use to actually plot the curve. Now notice .dist, that'll calculate either the cumulative probability or the height. NORM.INVERSE does the opposite. We will give it cumulative probability, the mean and the standard deviation, and it will tell us the x. So watch this. We're going to give it some probability, like 10% on the low end, and it will tell us what the x is. We can also do 1 minus 10%, and it will tell us, for example, the value that's the hurdle to get to the top 10%. So the inverses will get us our x. Now, these are x values. We're also going to want sometimes to deal with z values. Whoa, check this out. NORM.S for standardized value .dist. S.dist, we give it a z, and it will calculate either 1 for cumulative probability from the low end up to the z, or a 0, and it will calculate the height. NORM.S.INVERSE. We give it cumulative probability, and it will tell us what the z is. Scroll down here. The way I think of it is the .dist. This is when you have the x. The s is when you have the standardized value z. The .dist, that's what you use to get probability or height. .INVERSE for norm, or NORM.S for standardized value z. S.INVERSE, both of these inverse get you the particular value. Remember the key concept, from the low end up to the x. And we will see lots of examples. Here's our example we're going to do over in Excel. Professor looks at all test scores for particular tests. This is population data, and observes this pattern. Remember, the idea is if the distribution for the population follows a bell, then we can use the models. Now let's quickly look at the 3 types of probabilities we're going to calculate. Now, first, we might calculate probability that x or z will be less than or equal to a particular value. So we're going to know the value. And because With the normal distribution, it's area under the curve between two values. We're going to say everything less than some value. So if the test score is 64, the mean is 74, the standard deviation 10. Our z would be -1, right, because it's exactly 10 below. Here we're going to put NORM.DIST parameters in, and it will tell us the probability. So this answers the question, what are the chances that I will score 64 or less on a test? There it is. Second, we might calculate the probability that x or z will be greater than or equal to a particular value. So here we're going to throw in 80 and ask the question, what are the chances that I'll have a score 80 or above? DIST or S.DIST, they'll both give us the same answer. Probability, area under the curve. Notice it's 1 minus. We'll do these examples in just a second. The third situation is between. So I might ask the question, what are the chances that I will score between 75 and 90 points? Now, here's our rule for building our formula. It's always the bigger area minus the smaller area. So watch. All the area up to 90, that's going to be a big number. And then all the area up to 75. Well, if I take the big area and subtract the little area, that will give me the difference between the two. And that's the probability of getting between 75 and 90 on a test. Here's our formulas. It's going to be the bigger NORM.DIST minus the smaller NORM.DIST. Or if we're using z's, the bigger z probability or area minus the smaller z or probability. Scroll down here, and the last example we'll have to deal with is, what if we need to know an x? Well, notice here I want to know what is the score needed to be in the top 10% of the class. Remember, area under the curve is probability, so that is going to be equal to 10%. Well, if I can't throw 10% because remember the function goes brrrr, so the function would think you're right here. But if you do 1 minus, all of this is 90. And then it will spit out the z or x value. And we'll use NORM.INV when we want our x, and NORM.S for standardized z score, .inverse when we want our z. We'll either get points directly from our x value or number of standard deviations above. All right, now let's go over to Excel. And I want to first look at an example. We're going to talk about how the normal curve can move along the x-axis in accordance with moving the mean, or up and down in accordance with moving the standard deviation. Now, here's our situation. Ketchup bottle lists that it contains 20 ounces. Past historical data shows that the machine fills with a standard deviation of 0.2. So this is a manufacturer, right? Now, watch what happens when I change the standard deviation. You can see this curve. Right now, it looks like 19.4 ounces to 20.6 ounces gives us plus or minus 3 standard deviations. So I'm going to change the standard deviation to 0.1. And instantly, the spread gets much smaller. Now it's from 18.7 to 20.3. If I change it to 0.05 ounces, even smaller. So the standard deviation determines the shape or the height. I'm going to move this back to 0.2 ounces. And now if I change this to 19, watch right now. The mean 20 ounces for our x, 0 standard deviations or z scores for our z. If I change this to 19, instantly you can see the distribution moved. The shape didn't change. It just moved along this x-axis. There's 19, there's 0, and it looks like minus 3 standard deviations is 18.4, and plus standard deviation is 19.6. If I change this to 21, it goes up on the upper end. There's the mean. So the mean moves it back and forth. The standard deviation, move this back to 20. And the standard deviation, hey, look, there's much more spread out. 0.4, much more spread out. 0.5, it's getting fatter and wider. You could see at 0.5, that means plus or minus standard deviation would be all the way down to like 18.5, right? If we're counting by 0.5s, 18.5. 19 is minus 2. 19.5 is minus 1. And 20 is 0. All right, I'm going to change this back to standard deviation changes the shape or the height. Mean moves it along the axis. Now we're going to look at one example of each type of the probability examples. I'm on the sheet pop test data. Here's the data. So control down arrow, right? It's just the professor kept the data. When they plotted it, professor saw that it was a bell-shaped distribution. And so we can use the normal bell-shaped model. Now let's go over to the sheet norm less than or equal to. Now I'm going to show you how to draw this picture with a chart in the next video. But I want you to notice if we're asking the question, what's the probability that a score on a test could be less than or equal to 64? It means all the area this way. Even if you don't do it with the chart, you just do it on a piece of paper. Drawing pictures help. Now I want you to look over here. I'm going to right click Show Comment. So whether or not you're drawing it on a piece of paper, right, it helps to see all the way through Chapter 9 when we do hypothesis testing. These drawings for helping us with the normal bell curve for seeing the probability are really important. So it doesn't matter if you do it with a piece of paper or with your chart. Now here it is. Here's the mean. Here's the standard deviation. And here's our value. We want the probability less than or equal to that. Equals, and we have our x value. So it's NORM.DIST. Now notice there's a bunch of norm functions. All the ones with the yellow triangles are compatibility functions. We're not going to use any of those. We're going to use our 2010 or later function. DIST gives us the probability or height. Inverse will give us the actual x value. So our x, boom, there it is. Remember, this always goes from the low end up to our x. There's our x. Comma mean, comma standard deviation, comma and cumulative. Now these are the same names as last chapter when we were doing discrete, but they mean something totally different. Cumulative means doing integral calculus. This means the height of the curve. We're doing integral calculus, so I put true. Or as you've seen throughout all of this class, we use 1 for true and 0 for false. And that's it. That's the easy one. The probability is 0.15. Now if you want to calculate your z, equals open parentheses. I'm taking my particular x minus the mean, close parentheses, and divided by my standard deviation. This gives me -1. I'm exactly -1 standard deviation below. So if you have your z, we can use equals norm.s, and there's a dist and an invert. That s means you were doing z. Dist means I want the probability. So I'm putting in my z, comma 1 for cumulative, and it's going to give me the same answer as whether I use an x or a z. Again, I will show you how to plot this in the next video. Now I want to come over to norm greater than or equal to. So now we're asking the question, on the upper end, what's the probability of getting a score on this test greater than or equal to 80? I don't care if you draw the picture with the chart or if you come over here and draw the picture by hand. Nothing like drawing a picture to help us. All right, so what's the probability? So if I give it 80, it's going to spit out this. And since I want the upper end, I have to do 1 minus. So equals 1 minus norm.dist. There's the x. There's the mean. There's the standard deviation. Comma 1 for cumulative. Control Enter. That's the probability. About 27% chance that I could get 80 or above. Now our z equals, hey, I'm getting my particular x minus the mu, close parentheses, divided by my standard deviation. When I Control Enter, that tells me how many standard deviations above or below. I'm 0.6 above. Now I can use equals norm.s and dist. There's my z. Comma and cumulative. Guess what? If I enter this, this is not the right answer. This is the complement to that. That tells me from here all the way up to there. F2, so anytime you do that, oh yeah, I forgot, so 1 minus. And that's the upper end. You'll get the same exact number. Now we want to scroll over and talk about between. So here's our situation. I'm going between 90 and 75. So I'm trying to calculate the probability that I'll get a score between 75 and 90. draw the picture with the chart, that's fine. You can draw a picture on a piece of paper if you want, but drawing pictures really helps. Now here it is. We want to go from zip up to the 90, get all that area, and then subtract a second norm.dist zip that goes all the way to 75. So you ready? Equals norm.dist. The x, give me the big one first, comma, the mean, the standard deviation, comma, 1 for cumulative. If I enter this here, it's everything up to 90. So the probability of getting a score 90 or less is 0.94. F2, but now I need to subtract another norm.dist. I give it the smaller x, 75, comma, the mean, comma, the standard deviation, and 1. Two areas, bigger area minus smaller area, and that's the probability I get between 75 and 90, about 40%. Now if I'm calculating z equals open parentheses, my 75, that's the lower, minus, and I'm going to take my mean F4, close parentheses, divided by, and I want to divide it by standard deviation F4, Control Enter. So that's 0.1 above, just slightly above that 0, slightly above average, all the way to 0.16. I can see my cell references are working. Now I'm going to use the equals norm.S.dist. The bigger z, comma, 1 for cumulative from the low end, that gives me the probability of getting a z of 1.6 or less, F2 minus norm.S.DIST. And I'm going to put in the smaller z, comma, 1, close parentheses, Control Enter. I'm going to get exactly the same probability. 40% chance of getting a z between 0.1 and 1.6, or between 75 and 90 on the test. Now let's go over to find x, because here's the deal. Sometimes we're not after the probability, we're after the x. We know the probability under the curve, 90% below, 10% above. There will be some hurdle that will tell us and divide this in two. So our mean is 74, standard deviation 10, and we want probability on the upper end of 10% equals norm and its dot inverse. That will give us the x in this situation. Probability, if I give it just this, it'll tell me on the low end the number. That's not what I want. I want 10%, but please take 1 and subtract 10%. That'll go 90, all the way up to there. That's all the probability. That's what norm.inverse need. It needs the cumulative probability from the low end all the way up to the particular value you're searching for, comma, the mean, comma, the standard deviation, close parentheses. Oh, I love that. Now I know the score I need to be in the top 10%. If I wanted to get z, norm.s inverse, all I need is the probability, not the 10%. Please give me 1 minus the 10%, and boom, this will give me the z, 1.28. Again, draw a picture, whether you're doing it on paper or you're doing it with a chart. All right, that's a lot about the normal probability distribution. In this video, we talked about the characteristics of the normal distribution. We started out in Excel talking about calculating probability on the low end. Then we talked about probability on the upper end. We talked about between. And finally, we ended up with solving for an x or a z. All right, now when we come back in our next video, we're going to see how to create those charts. And then the video after that, we're going to have a bunch more examples of using the NORM.DIST and NORM.S.INV functions to solve problems. All right, see you next video.